Hello and welcome to this lecture. In this lecture, we're going to look at mostly computation of eigenvalues and some properties which are important sometimes in the computation. Most of the computation we'll look at by hand and how to sort of look at the matrix and maybe guess some of the eigenvalues, eigenvectors, etc. Okay, of course, today most people would use a computer to find the eigenvalues. That's okay, it's true. Eigenvalues and eigenvectors can be quite easily found with a computer, but sometimes you need to know about the eigenvalues based on structure and all of that. And so for that, it's good to reason about eigenvalues of a matrix. So we'll see how to compute eigenvalues, how to figure out eigenvectors by hand, and how to think of some properties of them. Okay, so let's get started. Okay, so from a high level, how do you do it by hand? If you have an n by n matrix, the eigenvalues by hand, if you want to do the best way to do it, the recipe is to look at the characteristic equation as it's called, which is determinant a minus lambda I equals 0. So this is a degree n polynomial in lambda, right? A is fixed, so if you actually multiply it out, you will get a degree n polynomial in lambda, and you can try to solve for it. Once you find the roots, you can find how many times the root repeats, and that would give you the algebraic multiplicity. So now of course for n equals 2, this is very easy. So once n becomes 3, it's not immediate. Many of us may not know how to solve cubic equations, let alone if it goes to degree 4, degree 5 or degree 100, right? So there's no way we can solve it. But nevertheless, this is sort of like the standard recipe. You should sort of know how this works. Sometimes you may be able to figure out things in some other fashion using properties. We'll see that later in the lecture. But this is the recipe for finding the eigenvalues. So note some of these roots may be repeated. So if they are repeated, then their algebraic multiplicity will increase. Okay, so anyway, you will have n roots, and remember, some of the roots can be complex also. Later on, we'll see some specific examples. Okay, what about eigenvectors? So now, once you have found eigenvalues, you can find eigenvectors. This is the recipe again. Given an eigenvalue lambda, how do you find the eigenvectors corresponding to them? The recipe is actually very simple. You only have to look for this matrix A minus lambda naught I. Now, what kind of matrix is this? So you have A. And when you do minus lambda naught I is diagonal, right? It's 1 on the diagonal. So this guy is lambda naught on the diagonals. So pretty much what you do when you do A minus lambda naught I is, from the diagonal values of A, you subtract lambda naught. Okay, everything else you keep the same. Okay, so this A minus lambda naught I is just that. You have a matrix A. From the diagonal values, you subtract lambda naught, you get a new matrix. And that matrix is guaranteed to be singular. Right? Why? Because determinant of A minus lambda I is 0 for every lambda, right? Every eigenvalue. So this lambda naught, A minus lambda naught I will be singular, meaning it will have a non-trivial null space, right? And you go find the null space. So every null space vector is actually an eigenvector with eigenvalue lambda naught. Of course, if you only look at non-zero vectors, remember, non-zero doesn't matter. Now, once you have null space, this is like a linear subspace, right? So you have a lot of vectors. So what people usually find is the basis, okay? So you find basis for this null space. You could find any basis, you can just generally find a basis. If you find a basis for the null space of this A minus lambda naught I, you get the linearly independent eigenvectors with eigenvalue lambda naught. Okay, so that's the typical recipe. So you give the eigenvalues, you find the eigenvalues, and for every eigenvalue, find a linearly independent set of eigenvectors, and number of linearly independent eigenvectors you have is the geometric multiplicity. Okay, so when you do that, you find also the geometric multiplicity. So what is geometric multiplicity? It's the nullity of this matrix A minus lambda naught I, which means it's n minus the rank of this matrix, right? So you find the rank of A minus lambda naught I, you do n minus that, you get the dimension of the null space, that is the nullity, and that's the geometric multiplicity. Okay, so basically the number of linearly independent eigenvectors that you can find for lambda naught is the geometric multiplicity. So this is like sort of the recipe, textbook method that you want to do by hand. Of course, there are a lot of shortcuts. We'll sometimes find the eigenvector first, right? We'll be able to find an invariant vector just by staring at the matrix sometimes, right? So you can do that first, and then you find the eigenvalue, and then maybe you go back to the characteristic equation, you know one root, you can factor it out, and then maybe you can factor. So you can do various tricks like that. We'll talk about it a little bit later on in this lecture. Okay, so this is the recipe. Okay, so let's see a whole bunch of examples. So we're going to see a lot of simple examples, and then just illustrate what are the sort of answers you will get, right? So it's important to look at that, and that's very important also. Okay, so how do you do this null space? You remember this method, right? So you do elimination for A minus lambda naught I. For small n, you can do it by hand. For large n, Anyway, for large n computers will use different methods to find eigenvalues and eigenvectors. Okay, so this is the recipe. Okay, here's the example. I'm going to start with a simple example, which is a 3 cross 3 triangular matrix, 1, 2, 3 on the diagonal, and then what is off diagonal doesn't matter. Okay, so if you do a minus lambda I, notice this lambda subtracts on the diagonal alone, so you get 1 minus lambda, 2 minus lambda, 3 minus lambda, and determinant is easy for a triangular matrix. It's just product of the diagonal elements, so it's 1 minus lambda, 2 minus lambda, 3 minus lambda. It comes out in factored form. You can easily read out the eigenvalue. So in general, we know that this is true, right? For a triangular matrix, the diagonals are the eigenvalues. Okay, so it just goes like this. It's a very easy to prove. I mean, easy thing to observe and prove if you want. Eigenvalues are just values on the diagonal. So it's just 1, 2, 3. What are algebraic multiplicities? 1 each, right? So every eigenvalue, 1 occurs with multiplicity 1, 2 occurs with multiplicity 1, 3 occurs with multiplicity 1. Okay, so eigenvalues are done. Very easy, right? So how do we do null space as an eigenvectors? Okay, I'm going to show it to you for lambda equal to 1 in some detail, and the other two we'll go through very quickly. Okay, so for lambda equals 1, I'm going to look at the null space of a minus I, isn't it? So I'm going to subtract a minus I. So from the diagonal, I'm going to subtract 1, right? So it's just minus I. So subtract 1 from the diagonal. So it will be a minus I will pretty much be a, except that the diagonals will be 0, 1, 2. Okay, and then I have to find null space, which means I have to solve this equation, right? A minus I is here 0, 0, 0, 0, 1, 2 on the diagonal, and then 1, 1, 1. Off diagonal elements remain the same. And you've got to do, you have to solve this equation. If you solve this equation, you get the null space, isn't it? x1, x2, x3 equals 0. So how do you solve it? You do elimination. So I've done this elimination very quickly. You can do it. You can do row exchanges and row combinations. You don't do column shifts. Okay, so don't do column shifts in this elimination. If you remember, that's how we do the null space. Once you do this, if you do column shift, you have to undo the column switch at the end, right? So remember that. So we won't do column shift, we'll just leave it like this. So you get this 1, 1, 1. How did I get this? So you can see I took the second row, subtracted the third row, and then subtracted from it the second row. So I got 0, 0, 2 I would have got, but then I can divide by 2, and so I'll get 0, 0, 1. So this is my reduced form. Now this one I have to solve. So if you solve this, so you notice here, so you have to sort of figure out what the free variable is, what the dependent variable is. So first thing you notice that x3 is actually determined explicitly, right? So x3 becomes 0, right? That comes out because of this, and then out of x1, x2 you can pick one of them freely. I will pick that x2, and the free variable you take it as 1 to get the basis, and that will give you x1 is minus 1. Okay, so this is the way to solve it. This is sort of like for every x2 you will get actually, so this will be an infinitely many solution, but it's only one dimensional. So the solutions are simply minus 1, 1, 0. So this is the basis for this null space. Okay, the null space of a minus I has basis minus 1, 1, 0. So any multiple of this is actually in the null space of this a minus I. You can go back and check minus 1, 1, 0. Right, minus 1, 1, 0. So if you subtract the first two columns, you should get 0. So that's the null space. Now you can sort of stare at it. You don't need to go through all this solution and the cancellation from here. You can easily guess it has to be 1, minus 1, 0. Right. So these two columns are identical. So it's 1, minus 1, 0. So these are the sort of tricks you can use to make your work a bit easier. So quickly we identified that this V1 was minus 1, 1, 0. So this V1 is the basis for this null space, and that will be the I vector that we will take, okay, as your eigenvector. So lambda equals 1, eigenvalue eigenvector is minus 1, 1, 0. Okay. So let's go to lambda equals 2. I've just gone through this very, very quickly. If you do a minus 2i, I'm subtracting minus 2 from the diagonal, so I'll get minus 1, 0, 1, and then this one, if you look at it, 0, 0, 1, 0, 0, 1, the second and third columns are the same. After you do all of it, the final solution has to be like 0, minus 1, 1. It can also be 0, 1, minus 1, both of these are the same, right? It's multiplication by 1, minus 1. So that gives you the same vector. So this null space of a minus 2i has basis 0, minus 1, 1, and that is the eigenvector we'll pick for eigenvalue lambda equals 2. Okay, easy enough, right? So notice how this a minus 2i, a minus I, all of them end up being singular. That's because this value is getting knocked out. That's how it will work. Okay, and lambda equals 3, again you get minus 2, minus 1, 0. I'm subtracting 3 from the diagonal. And here it may not be, here also it's very, very easy to figure out what the null space should be. I mean, you can go through the elimination process, but you notice here there's an all 0 column. So once there's an all 0 column, a null space basis is 0, 0, 1. Okay. Also, you see how I am figuring out the geometric multiplicity, the rank of A. Once I eliminate the rank of A is 2 here, it is again 2 here, it is again 2 here. So, 3 minus 2, 1 is the geometric multiplicity, and then you get the basis to be 0, 0, 1. Okay. So, I hope you see this. This is a very easy case where you found the eigenvalues and the eigenvectors explicitly. Okay. So, let us look at a slightly different case. So, in this particular case, I am looking at 1, 1, 3. So, I have a repetition here. So, I start having multiplicity. So, you notice here eigenvalues are 1, 1, 3. So, algebraic multiplicity of 1 is 2 and algebraic multiplicity of the eigenvalue 3 is 1, right. So, this is my eigenvalues. Okay, I did not write down the determinant A minus lambda and all, but anyway it is a triangular matrix, so the values on the triangle will end up being the eigenvalues. Okay. Now, let us do for lambda equals 1. Okay, now when lambda is 1, I am going to look at null space of A minus I have to subtract 1 from the diagonal. If I do that, I get 0, 0, 2. So, notice here this has rank 2, which means nullity is 1. So, this null space has only dimension 1. So, I am going to get only a one vector here, which will be the eigenvector. Okay. So, and here also you can figure out what it should be. So, 0, 0, 1, 0, 0, 2, the last two columns. So, it should be 0, minus 2, 1, right. So, ultimately you will get 0, minus 2, 1, that is your V1. So, this is your basis for the thing, and the geometric multiplicity of 1 ends up being 1. Okay. So, notice here how the algebraic multiplicity of 1 was 2, while the geometric multiplicity is only 1. Even though the eigenvector 1 appears twice, it has only one linearly independent eigenvector in as an eigenvector. Okay, you can't have one more. Okay, so here is a case where the GM became strictly less than the AM. Right, we always know that's true, but here in this case it became strictly lesser. Okay, so this is one example where you see that happens. For lambda equals 3, it's very easy. Again, the 0, 0, 0 will come, so 0, 0, 1 would be your eigenvector, and so lambda equals 3 has a geometric multiplicity 1. So, we know geometric multiplicity has to be at least 1, but it can be equal to 1, right. So, here is an example where it did not meet the algebraic multiplicity. Okay, so, let us go back and look at this example again. This 1, 1, 3, this value here, no, the second value I am going to make it 0. So, 0, 1, 1. So, in this case, notice what is going to happen. If you repeat the same thing as before, you do null space of A minus I, here you get a rank 1 matrix, right, 0, 0. Once you subtract 1 from the diagonal, you get 0, 0, 2, and then this value also I picked as 0, no, I changed it. So, now the dimension, the rank here is only 1, so which means the nullity is 2. So, your geometric multiplicity for the eigenvalue 1 now became 2, okay. So, you are going to get 2 linearly independent vectors, and you can guess very easily what they will be, like 1 minus 1 0, that will be one guy, and then 0 minus 2 1, that is the other one, right. So, these two columns can be subtracted, and this column you can multiply by 2 and subtract from this, and you will get 0. So, you get a 0 like this. So, you can go through the free variable sort of and then figure it out. This is another way of doing it. You can also, instead of doing 0 minus 2 1, you can also do minus 2 0 1, both are sort of equivalent. Okay, so, this is a basis for this null space. You can also have other type of basis, but notice you have 2 linearly independent eigenvectors now. Because I picked this value to be 0, I got 2 linearly independent eigenvectors. Okay, always remember, algebraic multiplicity is number of times the value appears as a root here. Geometric multiplicity actually depends a little bit more on the way the columns are and the rows are and what happens to the dimension of A minus I. When I subtract A minus lambda I, what happens to the null space there controls the geometric multiplicity. So, in this case, in this particular case, we got 2. In the previous case where this value was 1, right. So, when this value was 1, you got a 1 only here. Okay, so, you got 2, and 3 does not change, 3 is the same, you got the 0, 0, 0, and then 0, 0, 1 becomes your eigenvector for 3. Okay. So, hopefully these examples sort of showed you how the eigenvector can be computed by hand and what kind of answers you expect, right. So, you get geometric multiplicity and you get an algebraic multiplicity, and this could be lesser, greater, and you can extend this to various other types. Okay. So, I am going to stop here. So, hopefully this was a good illustration, and we will pick up some properties and some ideas and then try to apply them and maybe simplify our work or understand our work better. Okay. Thank you very much.